Okay, so in this video I want to talk a little bit about an example of generalized least squares fitting, and the example I used is just a linear fit based on 8 data points. So I'm looking at the average high temperatures for Renton, Washington, which is where I'm from, between the months of January and August, and I just picked up these this data off of Wikipedia, and I thought that would be a good way to show exactly linearly how average temperatures can change going from winter to the height of summer. Generalized least squares fitting can be used for other types of fits, if it's quadratic or if it's sinusoidal, anything. So in this case, if you wanted to go over the course of an entire year, obviously it's going to be low in January, go up in June, July, August, and then come back down. And so in that case, you would just use a different type of fit. In this case, though, we're using, for the sake of simplicity, we're using linear. And so as you can see here in this graph, it's just the scatter plot of the data points increasing over time, but not in a specifically linear way. In this one, you can see that there is an approximate linear fit that I drew. And the goal here is to minimize the square of the errors of the residual, and that r squared, the square of the errors is the coefficient of determination. So we're trying to find an r squared that is as close to 1 as possible, and if it's if r squared is closer to 1, that means the fit is better, or it fits the data the best and minimizes these errors that you can see. Are these little lines right here between the points that don't quite meet the graph or hit the line perfectly, but even the smaller ones will have tiny little ones. So the goal here is to minimize those, and you use generalized least squares fitting to do that. So this next one, this is kind of a brief overview of exactly what you do to do that. So because this is a linear fit, the only terms we need to use for the fit equation are y equals a0 plus a1x. a0 for this case is going to be the y-intercept through that fit for the fit, and then a1x is the slope times x, which is going to be all of our data points. And in this case, you use matrix math to do that. So the original equation is given z, a, and y matrices. Z is an m by n matrix, and m is the number of terms in the fit, which in this case is 2 because you have 2 terms here. And then n is the number of data points, which in this case is 8 because we have over the course of 8 months. Y is n by 1, and then a is m by 1 because those are the constants. And y is the data given in the data points in the y, in this case it's the temperatures. And so given the z, a, and y matrices, it's the transpose of z multiplied by z, and then that multiplied by a equals the transpose of z times y. In this case, because we don't know what the a's are, you would want to calculate for those a's. We can do that with matrix math, but it's also easy to just code that in MATLAB and it'll do that for us. And so in that case, you would move the equation around to have a equals the transpose of z multiplied by z to the negative first power multiplied, and all of that's multiplied by z, the transpose of z times y. And so here you can see the matrices fully formed. And so here, because of the way that the matrix math works, in the case of x, we're going by the months here, and because they're not actual data points, we're going by whatever month in the year it is. So because of the matrix math, there's no x multiplied by a0, so all of those are just 1. So that'll end up just being a sub 0, excuse me. A1 here is going to be multiplied by all of these data points. And so in this case, because in the chart it said January, February, and March, we're just moving up incrementally by 1 for each of those points, so it'll fit the best, or it'll fit ideally in the graph. And then the y matrix is the corresponding temperatures for each month. So January is 47, February is 51, and so on. And so that's how you form those matrices. So this ends up being A times whatever X value you have, and then this ends up being any of the Y's. If you think about it in those terms. And then, you know, it's data point 1, 2, 3, can't really read that. Whoop. 5, 6, 7, 8. And so that's how you form those matrices. So you can then compute that in MATLAB, like stick all those in there, do the math, and plot that. You can find the fit equation solving for the A's. Y equals 41.8571 plus 4.8095x. So the y-intercept for the sake of this fit is a of 0, which ends up being the 41.8571, and then a1, the slope of that fit, in order to minimize the square of those residuals, and then solve this over determined system, is 4.8095 multiplied by x. And so in this case, that's just 1. But then that will help achieve hitting all of these points much more closely and precisely. So you code that in MATLAB and create the plot. Here's what you come up with. So as you can see, there's the y-intercept down here, and then the slope here, you can approximate that at about 4 point, whatever that decimal point was that I've already forgotten. Anyways, and you can see that here, most of the data points here that have been plotted based on that data we used is as close to the fit as possible and minimizes these errors that you can see here, the divergence from that fit. And then from here you can also see that the coefficient of determination was calculated, and that's just a matter of doing series and using the mean of y and some other math that I really didn't want to go through by hand. But you can also code that in MATLAB. R squared here is 0.98732, and that indicates that because it is so close to 1, you know, if you round up, that's only about a little bit over 0.01 off. This fit is very accurate, or very close to being as good of a fit, or being as close to a perfect fit for this data. Obviously, it can't necessarily be perfect because of the divergences in some of the data points. It just doesn't work linearly, or as linearly as we would like, because some of them are a little bit too close. But at the same time, because it is so close, we can tell that this is still a good fit for these data points. If it were closer to 0, we probably wouldn't want to use it. If we wanted to, like, this isn't how weather works, but if we wanted to say, like, oh, in mid-February, what temperature might it be? It might be around here, who knows? But you can still see, like, the projection of the increase in temperature from January to August. And then over here, it's going to start to, like, go down a little bit, because then you'll hit September, October, November, December. But that, for the sake of this, doesn't matter. Anyways, so that's how you use generalized least squares fitting to create a line fit for a series of data points. And in this case, it's just linear, but again, if you had, like, data points that were, like, something like that, you could still do, like, a sinusoid, or you could do a quadratic, or anything like that, as long as you know what the appropriate equation is. That's not very straight, but you understand what I'm talking about. Anyways, so that's how you do it. Thank you.